All right, so today we're going to learn how to solve a system of equations by substitution. We've already talked about how you can graph the two systems and you can see where they intersect with each other, and that single point is going to be your solution set. Okay, so we're going to look at a way that you can do that without having to pull out a piece of graph paper and take the time to graph every single equation that you come in contact with. Okay, so we have two equations here. I could change those both to slope-intercept form and then graph them and see where they intersect, but I'm going to show you how to do that without. So the first thing that you're going to want is you're going to make sure one of your equation is in slope-intercept form, or y equals. You want the y by itself on the left side. So we're going to decide which one of these is going to be easier to make that happen. We're going to go with this one here. So whenever I move the x to the other side, it's going to leave me y all by itself, which is exactly what I need. Okay, it doesn't matter how this side looks. It doesn't matter if the constant's first or the variable. It isn't going to matter. So we're going to say, okay, if y is 3 minus x, that's what y stands for. Y is 3 minus x. Then we're going to take that value of 3 minus x and we are going to substitute it into the other equation. Okay, so if we know that y is 3 minus x, we're going to take that up here and we are going to plug it in for y. Okay, so I'm going to change colors so we can see this here. So that means I'm going to now have an equation. I'm going to take this top equation, but everywhere I see a y, I'm going to put what y represents. And y represents 3 minus x. So my equation is going to look like 2x minus 3y, but instead of y, I'm going to put what y represents. We're going to use parentheses here, and then equals 21. So I have taken the top equation, and I have just simply inserted what y represents, okay? So then I'm going to solve. I'm going to solve, and I'm going to get an x value. So this is just like solving an equation. I'm going to do it really quick. Add 9, so 30, so x equals 6. Okay, so solve it like an equation. I get that x equals 6. Now, if you remember when we were solving systems before, we were graphing them and we were picking out the single point where they intersected, which means my answer was an actual point. So my answer is an x comma y value because it is a point on the graph where the two lines are going to intersect each other. Well, all we have so far is an x value, so we only have half of our answer. So my answer is 6 comma something. I'm just not sure what the y value is yet. So I've got the x coordinate. I need the y. So what I'm going to do is I can choose any of these equations that I want to take 6 and plug it into. I can choose this original equation that's in standard form. I could choose this original equation that's in standard form, or I can choose this equation after I put it in slope-intercept form. I personally like to use this one because to me it's just a lot easier. I don't have to do any manipulation. I just plug it straight in. So this equation says y equals 3 minus x. So I'm going to take my x value of 6 and I'm going to put it here. So y is going to be equal to 3 minus 6. Okay? So that means that y is going to be equal to negative 3. So that's the y coordinate of my answer. So my final answer is the point 6 comma negative 3. If I were to graph these two original equations that I had, they would intersect to the point 6 comma negative 3. That means that this x value, when you plug it in, and this y value, when you plug it in, you're going to get a true statement. So I could take 6 negative 3 and I could plug it in to the first equation, or I could plug it into the second equation, and it's going to work for both of them because they intersect each other at that single point. And that is the solution to a system. So this is how you would do substitution. Make sure one of your equations, you change it to slope-intercept form, take whatever that y value is equal to, and plug it back into the other equation. All right, let's look at another example of substitution. I told you on that last problem that you wanted one of your equations to be in slope-intercept form, which is y equals something. I told you that you wanted that y value on the left side of the equation all by itself. And that's true, but it could also be that the x is on the left side by itself. It doesn't actually matter if it's the x or the y on the left side by itself. You just want one of the variables isolated already. So in this case, I wouldn't take the time to move y back over so that it would be on the left and then move the x over here. I don't need to take the time to switch all that around. I've got one of these variables isolated by itself, which is all I need. So that means in this case, we're going to see what x represents and we're going to plug in for x. So if x represents y minus 7, then I'm going to take that value and I'm going to plug it in for x of the original equation. Okay, so my equation is going to look like this. I'm going to look at this top equation and I've got an x first, but I want to talk about what x represents. And x represents y minus 7. So I'm going to put that instead of x. Plus an 8y equals a 2. So this is my top equation with that x value plugged in for x. So here I'm going to solve and I'm going to have 9y is equal to 9. So y is equal to 1. Now this again gets me half of my solution, but only half. So this tells me that the y value of my solution is 1. So I don't know what x is, but I know that my y is 1. So from there, I would take the fact that y is 1 and I would plug it back in to this equation that was already isolated for me. So I have x equals y minus 7, so 1 minus 7, because I'm taking the y value and plugging it in. So x is going to be equal to negative 6. So negative 6 is the x value of my solution set, and there would be my solution. All right, we'll do one more example. Here I have two linear equations. They are both in standard form. I need one of them to either be x equal or y equal. So when I'm looking, I see that the second equation is probably the least complicated equation just because I see less coefficients. So when I look at this, I say, okay, well, should I try to get the y all by itself or should I try to get the x all by itself because it doesn't really matter? In this case, I would say choose what you think is going to be the easiest for you. If we tried to do y by itself, it would require us moving the x over as well as dividing everything by the negative 3. But if we tried to get x by itself, all we would have to do is move the 3y over. To me, that's a little bit easier because it's only one step versus two steps, and it doesn't matter which way you do it. So I'm going to go with x equals negative 3 plus 3y as my equation. So now this is the equation that I have manipulated, and this tells me what x is going to represent. X represents negative 3 plus 3y. So when I go back to my original equation, I'm going to plug this value in to represent the x. So let's look at our first equation here that we have not touched or manipulated. It is 2x. So I'm going to put 2, and instead of x, I'm going to put what x represents. And x represents negative 3 plus 3y. And you definitely want to use parentheses. Then I've got a plus 5y. And then I've got an equals 38. And now I just have a typical equation that we've been working on since the beginning of the year that I can solve. And I'm going to end up getting y equals something once I solve. So y equals 4. So that's going to be half of my solution. I don't have an x value, but I know that y is 4. So I'm going to take that 4 and I'm going to plug it back in. So remember I told you I like to plug it back into this equation that I manipulated because it just is easier. So I have negative 3 plus 3 times the y that I just found. So that's negative 3 plus 12, which is 9. So my x value is 9. and my solution is going to be 9, 4. This would be the point where these two original equations, here's the first one, here's the second one, these two original equations would intersect each other if you were to graph them.